So a body at rest is given an initial uniform acceleration. Initial uniform acceleration of, so initial acceleration of the body is 8 meters per second squared for 30 seconds. So this uniformly acceleration happened for 30 seconds. After which the acceleration is reduced to 5.0. So the second acceleration A was reduced from 8 to 5.0 meters per second squared for the next 20 seconds. So T2 for the next 20 seconds, we have this. Then the body maintains the speed attained for 60 seconds. So the speed attained after reducing the earlier acceleration to this, it was maintained for, this is an unknown speed, but we are told it was maintained for 60 seconds. So T3, 60 seconds. After which it is brought to rest in 20 seconds. So the fourth part of the motion was that the body was brought to rest, meaning the final velocity here is 0. Then for a time period of T4 of 20 seconds, okay, we have to draw the velocity time graph of the motion using the information given, and then solve the questions that follow. So this is it. Now, let's look at when a body accelerates. Acceleration goes with an increase or increment in speed. So when the body's initial, we are told the body starts from rest, meaning that the initial velocity is 0. So if it is starting from rest, then U1 is equal to 0. If U1 is 0 and it accelerates uniformly at 8.0 meters per second square within a time of 30 seconds, what will be the final velocity? So V1 would be equal to U1 plus A1T. I'm using 1, 2, 3 to denote first part of the motion, second part, third part, and then the fourth part. Okay, so V1 will be equal to, the body start from rest, so U is 0 plus acceleration of 8 meters per second squared for 30 seconds. Okay, please, when you come in, mute yourself. Mute yourself. This is giving us a final velocity of 240 meters per second. Now from there, the body's acceleration was reduced to 5 meters per second squared. Class, a drop in acceleration isn't a deceleration. Okay, when a body is uniformly accelerated, we all understand that the body moves with a certain velocity, constant velocity or uniform velocity within equal time interval. So maybe the body is moving with a velocity of 10 meters per second within equal time interval. So 10, 20, 30, 40 within every second. If the body drops acceleration, then the thought is that, okay, then let me change my equal speed or velocity from 10 to maybe 8. So from 8, 16, 24, on and on and on, meaning I'm dropping the speed. This is not deceleration. If it's a deceleration, it will be reducing speed in the opposite direction. So when I'm moving from left to right with that constant velocity within equal time interval, if I'm decelerating, I'll change direction from right to left and then reduce the speed. But if acceleration is reduced, it simply means that the speed is reduced in that specified direction with time interval. Please, are we okay? Are we okay? And I'm stressing on this because when I looked at the solved your solution, I saw a deceleration just because the statement said that acceleration was reduced. Please, I hope you're okay.
Yes, please.
All right. So if this time the acceleration is reduced to 5, what will be the final speed? Don't forget, it's a continuous motion. It's a continuous motion. So the final velocity of the first part becomes the initial velocity of the second part. So it means that U2 will be equal to V1, which is 240 meters per second. So if the starting velocity for the second part is this, what will be the final velocity V2? V2 therefore becomes U2 plus A2 times T2. And this will be equal to 240 plus an acceleration of 5 times a time interval of 20. So we have 340 meters per second. Say this is 100. So that will be the final velocity when the acceleration is reduced from 8 to 5. Then in the third part of the motion, we are told that the velocity was maintained for 60 seconds. If velocity is maintained, it means acceleration is 0. Okay, so it simply implies that U3 is equal to V3 within a time interval of this is equal to 340 meters per second. And this happened within a time interval of 60 seconds. Then from there was a uniform deceleration. This velocity V3 reduced uniformly till it got to 0 within a time interval of 20 seconds. That is what the information or what the question says. Please, if you have any question, bring it up before we look at what we have to calculate for. Do you have any question? Any clarification to be given here? Okay, so draw the velocity time graph of the motion using the information given above. Draw the velocity time graph. So it's just a sketch. We are not drawing to scale, so I'm sketching a velocity time graph. So time slash seconds, then velocity v slash meter per second. We are starting from a velocity of 0, then we go to a velocity of 240, then a velocity of 340. Okay, then a time interval of, in the first part of the motion, we have a time interval of 30 seconds. So from 0 to 30. Then the second part of the motion, time interval of 20 seconds. So 30 plus 20, giving us 50. Then the next time interval 60. So 60 plus 50, 110. Then the final part of the motion, we have a time period of 20 seconds. So this is 20. So 110 plus 20, giving us a total time of 130. So let's plot the first part. The body was uniformly accelerated within 30 seconds, attaining a final velocity of 240. So we have this time matching a velocity of, and the motion starts from rest. So it must start from a point where initial velocity is 0. Then the acceleration was reduced to 5 meters per second, okay, within a time interval of 20. And when that was done, the final velocity attained is 340. On a graph, when acceleration is reduced, it is shown by a drop in the slope. So this must have a lesser, the second part of the motion must have a lesser slope, 50. So the slope of this first part is greater than the slope of the second part, denoting a drop in the acceleration. Okay, then the third part of the motion, the velocity was maintained for 60 seconds. So for 60 seconds time interval, velocity was maintained. Time, so the gradient or the slope is 0. Then finally, the velocity was reduced to the point where it came to a stop. The body came to a stop. So we have a uniform deceleration to a point where the velocity is 0. And velocity is 0 in the time axis. So this is the graph of the motion. This is the graph of the motion. Please, do you have any issue with the graph? If you have any question concerning the graph, let me know. Or you are okay?
Please, can you go by it again?
Okay, so after calculating for the final velocity at the first part and second part of the motion, we got final velocity of 240 when the acceleration was 8 meters per second square. Okay, then when the acceleration was reduced to 5, we got a final speed of 340. And we have to sketch a velocity time graph. So here we are looking at the velocity of the body within every time interval. So within the time interval 0 to 30 seconds, the body went through a uniform acceleration of 8 meters per second square. And so the time interval against the final velocity attained. So from when the velocity was 0, when the initial velocity was 0 to when the final velocity is 240 for the first part of the motion. So this is for 1, indicating the first part, second part, third part, and then this is the fourth part of the motion. Okay, then from the second part of the motion, the body's acceleration was reduced to 5, from 8 to 5. And when we calculated that, we got a final, when the acceleration was reduced to 5, we had a final velocity of 340 meters per second. So in the second part, when the starting velocity is 240, we are getting a final velocity of 240. And this happens within a time interval of 20 seconds. So 30 plus the 20, giving us a total time of 50. Okay. The slope of this indicates the acceleration. But since the acceleration of the first part is greater than the acceleration of the second part, the slope must drop. When I draw a steepy line and then a lesser steepy line and a velocity time graph, it tells that the acceleration of this is greater than this acceleration. And that is what has been shown here. Okay. And so the final velocity is 340 within a time interval of 20 seconds. Then in the third part of the motion, we are told that the body's velocity was maintained. The body moved with a constant velocity for 60 seconds. So 60 plus 50, giving us a total time of 110 seconds. Okay, so within this period, 60 seconds, the velocity was constant. Then the final part of the motion says that the body's, after which it is brought to rest. After this, the body was brought to rest in 20 seconds. When a body is brought to rest, it means it is coming to a stop where its final velocity is 0. So within 20 seconds, 110 plus 20, giving us a total of 130. The body speed was reduced till it came to a stop where the final velocity is 0. And this is the velocity time graph of the motion. All right. So using the graph, calculate the maximum speed attained during the motion. Calculate the maximum speed attained. So when you look at the graph, the maximum speed attained during the motion was equal to 340 meters per second. During the whole motion, the maximum speed attained was this. 2. Calculate the average retardation as the body is being brought to rest. Calculate the average retardation as the body was being brought to rest. If you have a velocity time graph or speed time graph, the slope is equal to the acceleration. Okay, acceleration can be positive or negative. When acceleration is negative, we call that as deceleration or retardation. Okay, so the average retardation or deceleration is equal to the slope, which is the change in the vertical over the change in the horizontal, which is time. Now, what is the change in the vertical? This is the initial speed, and then the final speed is 0. So 0 minus 340 over the time interval within which this happened is 20. So minus 340 on 20. This is 34 over 2. And what is 34 over 2? Plus, what is 34 over 2? Yes, what is 34 over 2?
17.
So we have minus 17 meter per second square. So the average retardation is 17 meter per second square. In fact, if you bring negative, you are not wrong because a retardation or deceleration is negative. But if you write 17, then you are giving the magnitude, the absolute value without the negative, period. Then calculate the total distance traveled during the first 50 seconds. The total distance traveled during the first 50 seconds. So over here, the question doesn't demand the whole distance covered. It is only interested in the distance covered during the first 50 seconds. So we are only limiting ourselves to this shape of the graph. Okay, we are only limiting ourselves to this shape of the graph. Do not calculate everything, no. During the first 50 seconds. Then, for a velocity time graph, the area under the graph is equal to the total distance traveled. So it means that to find the total distance, I just need the area under the graph between the time axes. So I have two different shapes. I have 1 and then 2. Somebody can also see this as 3 different shapes. Whichever way you look at it, the value is the same. It won't change the results. I'm seeing 2. I have a triangle and then a trapezium. So total distance covered . Total distance covered is equal to, this is a triangle. So half base, the base is 30. The height is 240 plus, this is a trapezium, half A, this is the side A, 240 plus the side B, this is the side B, 340 times H. H is the height which is perpendicular to both A and B, and this is the side. This side is perpendicular to both A and B, and this is 50 minus 30, 20. So times 20. So in all, we have, I want you to quickly calculate and tell me. Make the calculation and then tell me. Okay, Paulette, what have you had?
Please, I got my final answer to be 9,400 meters.
Okay, let's see. So I have 58003600. Okay. So this is 49. Thank you. So we have 9,400 meters as the total distance covered during the first 50 seconds. I want you to calculate the total distance covered during the whole period. Do that for me. The total distance covered during the whole period. Or during the whole or the motion. So an extra word given to you. So I'm waiting for you. In about 2-3 minutes, I'll come to you. So the total distance covered during the whole period. So 3 minutes in. Leslie, mute yourself. Leslie, mute yourself. Leonard, mute yourself. Are you true? What have you had for the total distance travel? What have you had? Yes. Yes, Paulette.
So please, I had 4,200 meters.
4,200 meters. Paulette, as the total distance during the whole journey.
Oh, sorry, that's just for the other one. I'm yet to add the 9,400.
Okay. All right. Okay, so I think what Paulette did was this. She calculated for this remaining side. Okay, since we have the total distance covered for the first 50 seconds, she calculated for the total distance for the rest of the seconds. The next 100 and the next 80 seconds. So when we go by that, this area is a rectangle. So we have 340 times 60, giving us this area. Okay, then this is a triangle, half times the base. The base is 20 times the height, which is 340. So we have what is 34 by 6? Multiply 34 by 6 and tell me.
200 and
200 and what?
204.
204.
204 0 plus this is 3400. So 204 plus 3400. We have 00832.
23,800.
5,800.
Is that correct?
Yes, sir.
Class, is that correct?
Yes, please.
Yes, please.
So
Yes, please.
let's add 9,400. 002 21. So we have 3. Okay, 3 as the total distance traveled. Is that what you got?
Yes, please.
Yes,
All right.
please.
Okay, so if we are to look for the total distance traveled, then this is how we go about it. You segregate it into different areas, and then that is it. But the question demanded the total distance traveled during the first 50 seconds. All right. Now, what is the last question? The last question demands that we find the average speed during the same interval. Here, I'm adding 2 things. Find the average speed during the same interval as in II, and find the average speed during the whole motion. So I'm adding another one. Find the average speed during the said time interval in II during this distance traveled, and then find the average speed for the whole motion. Start with 3 minutes. 3 minutes. In 3 minutes time, I'll come back to you.
Repeat the question again.
You are looking for the average speed during the same time interval as in II. It refers to this total distance traveled. And what I'm adding on is that find the average speed during the whole motion, during the whole period of the motion of the body.
Okay, thank you.
Yes, Camille, your hand is up. Yes, Camille, go ahead. Oh, maybe it's he's not aware. Okay. Well noted. All right, I think your time is up. What did you go for the average speed during the interval in II? Okay, we don't have time. Average speed is total distance over the total time. So 9400 is the total distance over a period at a time interval of 50 seconds. Okay, so 940 divided by 5. Elinam, mute yourself. Elinam, what is 940 divided by 5?
1,880.
Come again.
1,880.
No, 940 divided by 5. Leonard, your hand is up.
So please 188.
188 meter per second. Yes. And then what is the average speed during the whole motion? What did we get for the total distance? Joel, what did we get for the total distance? 13. Is it 13,300 and something? We just calculated, those of you who recorded it.
Yes, we got 33,200.
Good. So this divided by a time period of 130 would give us the average speed during the whole time interval. Please, are we okay? All right. Please, any questions? Joel, mute yourself. Let me mute all, rather. Please, if your hand is up, go ahead with your question. If your hand is up or you want to clarify something quickly, go ahead with your question before.
So I wanted to mention the answer.
Oh, okay. What have you had?
255.4.
455.4 meters.
255.
Okay. So 255.4 meters per second is the average speed during the whole motion. Please, the average speed is a quantity which describes how fast a body moves. So if you want to describe how fast a body is moving within a given time period, that is when we talk about its average speed. Take notes. So put it down. It's a quantity which describes how fast a body is moving, right? Within a given time interval. Okay, so as I said earlier, our next point of discussion is vertical motion under gravity. Vertical motion under gravity. We've done linear motion, but we restricted ourselves to uniform accelerated linear motion. So as I said earlier, the three equations of motion applies to when the body is uniformly accelerated. Meaning, if the motion is not uniformly accelerated, you cannot use the equation. So there are limitations. The limitation is that the equations works with uniformly accelerated linear motion. And that is what you must know at your level. At your level, you don't look at non-uniformly accelerated motion. So uniform motion and or vertical motion, and gravity. Let me begin this by asking, when you stand on a tower and you drop a coin and then a hammer, a coin, and then a hammer. Which one drops first? Yes. Okay. Leonard,
Sir, please, the hammer will drop first.
the hammer drops first. More views. Paulette. Okay, Josiah, I've taken note. Paulette, what do you also think? Oh, Gabby. Gabby, take over. When you drop
Sir,
a
please, the hammer
hammer,
will go first.
okay, the hammer drops first. All right. You see, the hammer drops first because we are not taking out a certain factor. The hammer drops first because we are not taking out a certain factor. Now, if we take a factor out, that is when we manage to neglect air resistance, or when we go to a place where there's no air blowing, both objects drops at the same time. I'm taking it again. The hammer will drop first when there is air resistance. So if there is moving air, the air around is being disturbed and is blowing. When you drop a hammer and a coin, the hammer certainly will drop first. But when we manage to take out air resistance, or a place where there is no air blowing, okay, and then you drop a hammer and a coin, both bodies drops first or drops at the same time. And this is an experiment that was conducted by the then scientist Galileo on the Tower of Sicily. Galileo stood on the Tower of Sicily and dropped two objects of different weights and so of different masses, under the condition that air resistance was neglected, or air resistance was very, 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 very negligible. Virtually, there wasn't any air movement. And when he dropped two objects of different masses, he realized that the objects dropped on the ground at the same time. It was also conducted on the moon by an astronaut. In fact, the name has just escaped me. The name of the astronaut. When it comes, I'll tell you. But he dropped a hammer and a coin on the moon. And both of them, both the hammer and then the coin, dropped at the same time. Is that okay? So a denser object and a less dense object, when dropped, can drop simultaneously at the same time under the condition that air resistance is neglected. If you don't do that under that condition, the heavier object or the denser object drops before the less dense object. Please, is that okay? Class, is that okay?
Yes, please.
All right, so please, if you have any question, ask. Okay, so with vertical motion under gravity, we are looking at an object dropped in this direction. This is from up, down. And we'll also be looking at an object projected or thrown from down, up. So two different situations will be considered. Now, if an object is being dropped, so vertically, let's look at vertically upward motion. Vertically upward motion. Here we are, the object is being thrown down, up. So we are moving in this direction. We are moving in this direction. Down, up. Now before, and please, we are doing this by neglecting air resistance on the assumption that air resistance is so negligible. That is the condition. Before an object can be thrown up, the object by itself cannot go up. I can hold this and then by magic, this object is going up, being levitated. No. Before it can go up, an external force must act on it. So there must be a force. The force gives the object a certain initial velocity. So an object projected upwardly has an initial velocity u by the application of an external force. So an object thrown upwardly has an initial velocity u by the application of an external force. But as the object goes up with time, as time changes, what happens to the object? Yes. So when an object is thrown and is going up, ladies and gentlemen, what happens to the object as the object goes up? Share your experiences with me. Elinam, Elinam, go ahead.
Sir, please, when it reaches a certain point, the object will stop for a couple of seconds, then it will come back down.
So what causes, okay, you have given us what you think. Let me attend to somebody else. Yes, please, if your hand is up, go ahead.
Sir, please, because of the force applied when throwing the object upwards, it goes at a certain speed. Then at a point, it stops, then comes down at a very high speed. It depends on how far or how it went.
Okay, so, okay, my point of interest is that as the object goes up, what causes its velocity to drop? Or what causes it to stop at a certain height? What causes its to stop at a certain height? That's my question. Yes, if your hand is up, one.
Surface
Yeah.
gravity.
All right. Okay.
Yeah.
So gravity. Gabby, do you have something to say?
Yes. And because it's going against gravity.
Okay. All right.
Because it's moving up, it's going.
Okay. So the force gives it an initial or starting velocity u, but because the object moves against gravity, as you said, okay, force, gravitational force. So it's like one force wrestling with another force, okay, upward force battling with the downward force. Okay, so gravity reduces the force and the speed. So it comes to a point where the speed, the initial velocity of the body is reduced to 0. Then the body, we say, reaches its maximum height. So whenever an object is thrown vertically upward, okay, when it gets to the maximum height range, its final velocity there must be 0. So technically, what we are saying is that an object projected vertically upwards decelerates because we are talking about a reduction in its velocity. U very high, but as the object moves with time, its velocity will be reducing. So if the velocity is reducing with time, then the body is decelerating. Okay, so it decelerates, but this deceleration is caused by gravity. So we technically say that an object projected vertically upward decelerates due to gravity. All right. So the object projected upwardly decelerates due to gravity. And reaches a maximum height. So it decelerates and then reaches just to a maximum height where the object's final velocity is 0. All right. So if the body is decelerating, then we must have an equation which describes its velocity with time, because we realize that the object velocity will change with time. So at 1 second, 2 seconds, 3 seconds, we can calculate the velocity of the body. Then we can also determine the distance, vertical distance traveled with time. All right. So let's look at equations of vertically upward motion. So equations of vertically upward motion. We can have mathematical equations to describe the rising or moving objects with time. So if we want to calculate the velocity of the body after any time t, but we understand that as it is going up, its velocity decreases with time because it decelerates, and this deceleration is due to gravity. So equation 1, equations that are used to describe this kind of motion is similar to whatever we have for linear motion. Let's recap what we got for linear motion. What are the 3 equations of motion we derive? Equation 1. What is the first equation? Yes. What's the first
V
equation?
is equal to
V is equal to
U plus 8.
good, U plus 80. Then 2. Josiah, I've seen you. What's the second one? What's the second equation? Hey, Angel and Paul, Eva, Ayo, Nana Kwame, Jojo. Yes, please, if your hand is up, go ahead.
S is equal to UT plus AT squared over
What? 2. Then the last one. Yes, Elena, go ahead. Elena, go ahead.
Sir, please, V squared is equal to
It's equal to, let's not wait time. U squared plus 2AX. All right. So please, the difference here is that in equation 1, 2, 3, this acceleration is due to the contact force between the body and then the ground. Linear motion, this is about linear motion. So the acceleration A, okay, is due to the contact force between the body and then the ground. Okay, but in equation, in vertical motion and the gravity, the acceleration is due to gravity. So V equation 1, V is equal to U. Now over here, the body accelerates, a positive acceleration. But when an object is projected vertically upwards, the body decelerates. So the deceleration, which is due to gravity, and deceleration or retardation is negative. So minus A changes to G because the deceleration is due to gravity, force of gravity. So we make that changes, A for linear and then G for gravity. So minus GT. This is equation 1 for vertically upward motion. Then for a vertical height traveled by the body, we won't use displacement, but we'll use height, h. So S changes to h because we are talking about vertical height travel. So h is equal to ut. This acceleration is a deceleration due to gravity. So minus half JT squared. That is equation 2. Then finally, V squared is equal to U squared. The acceleration over here is a deceleration due to gravity. So G is negative, and so it will affect the entire operator here. So still minus 2J/H. These are the three equations of motion when it comes to vertically upward motion, where V is the velocity at any time t. Is the velocity at any time t. U is the initial velocity. Before the object can go up, we must give it a certain initial velocity, U. J is the acceleration, okay, due to gravity. But because it's a deceleration, the reason for the negative here. Okay, so usually, why is this negative? We don't mean because the body's motion is against gravity, but we say that it is negative because the body decelerates, okay, when it is moving vertically upward. And this deceleration is due to or caused by gravity, the reason for which we indicate minus J. Okay, fine. When you say it is moving against gravity, it's true. But then technically, mathematically, this is what we mean. Please, any question? Any question here? No.